everyone. Welcome to the AWS Webinar Week. Today we're going to talk about best practices for performance scale on MySQL using the relational database service in AWS. So what is new? Let us start off with what is new on RDS. So we have a new region, Frankfurt. We have RDS available there. You can start using RDS today in Frankfurt. We support general purpose SSD storage for our RDS instances. If you have not already migrated to SSDs, please migrate to SSDs from magnetic storage. We support newer instance types, namely the M3s, the R3s, and T2 instance types. These provide better performance for the dollar. And we also support cross-region replication. We are giving you a single-click upgrade from 5.5 to 5.6 and also InnoDB cache warming. I'm going to talk about how to scale your RDS instances for the next 45 minutes. And as we progress with the webinar, please feel free to post your questions onto the chat window, and we're more than happy to pick up questions and answer them. So, selected RDS customers in the world. You must be knowing a lot of names here. We have Flipboard, we have got NASA, we have got Lamborghini, Intuit using us today. So, what is with data migration? How do I migrate data from my existing MySQL instances into RDS? These instances can be running either on-prem or on EC2 instances as well. So, your app is now currently talking to a DB master. You can take a backup from the DB master, or better still, take a backup from the slave. If you have a slave running for the DB master, take a backup from the slave, ship this backup to a staging server in AWS. Shipping the backup is as simple as doing a SCP from your backup server into AWS EC2 servers. Once it is there on the staging server, you can import this data into a slave database. Why do I call it a slave database? Because once the data has been imported, I'm going to make this a slave to the master on your on-prem. So the replication starts between DB master and the slave. And once the replication lag hits 0, when would the replication lag hit 0? It will hit 0 when your application is having the least number of users. So you have the low number of transactions happening. So your application lag will hit 0. Once your application lag hits 0, you can convert this database to a master, connect it to your application running on EC2, and then start using it. So once this is a master, what happens is your application ceases to function on-prem or on EC2, and then your database is now migrated to AWS. So what are the best practices that you need to consider when you're moving an external MySQL source into RDS? Take backups from a replica or slave. That's always better, so that you don't have to take it from your master and pollinate your master with the backup requests. Always try to compress backups for faster transfer. We do provide you the import-export service where you can import your data into AWS using hard disks shipped to us. But I would suggest you compress your backup, and your usual MySQL dumps can be compressed to a far greater extent. And once the backup is compressed, it will be very easy for you to transfer it over the wire, over the internet. Use a staging server on Amazon EC2. Don't try to do your import of RDS from your on-prem directly into RDS. Because this is going to be over the network, and if your network has a jitter, you will find that your backups, your import stops, and you'll have to start from beginning. And that's not a very good way to do stuff. And it's always better that you move the bulk of the data into AWS and then use the best network performance we give you between EC2 and RDS to import the data from your backup into RDS. Use the primary key sort order where possible so that your data is less defragmented inside the database. And what are the considerations you need to have for RDS instance on AWS, the instance into which you are going to import the data into. Use more memory and IOPS so that you can get faster loading. You can always scale back down. So you can start off with a bigger instance with a bigger IOPS and then scale back down to a smaller instance as your transactions deem fit. The number of transactions per second your QPS deems fit. You can actually downgrade your server online with RDS. So please start off with more memory and IOPS so that your loading is faster. Disable multi-AZ on the RDS configuration. Disable binary logging, which is basically saying that the backup retention is 0. So don't take any backups on the slave. So your load operation will be very fast if there is no binary logging happening. And there are certain MySQL considerations you may want to do. You may want to do INODB flush log at transaction commits. You may want to set it to 0 so that you don't want to flush your logs at every commit. So that the flushing of logs is a read-write operation onto the database, and that takes time. You can avoid doing that. Set the auto commit to 0 as well. Set the unique checks and foreign key checks to 0 so that you don't have to perform those checks, because your data is coming from a database that is already having these checks enforced. So you don't have to perform these checks. And increase the INODB log file size. This is available in 5.6, and this helps you to contain more in the log file so that there is not much flushing happening on the log file. The log file needs to be flushed at frequent intervals for crash recovery purpose. So instead of actually keeping the INODB log file size at a small level and flushing it frequently to the disk, it is better that you have bigger log file size so that the log file size when they get flushed from memory, they can accommodate more, and at the same time they don't rotate too very often. So what are the input formats that we can do with the import utility? The standard MySQL dump out, you can do a load schema data, auto on off, and index and constraints. So the MySQL dump output is there. The other way to do it is using the MySQL dump, but using the flag to fields terminated by tab or comma or whatever special character you want to do there. And then you load the schema and data separately. So that you load the schema separately from your schema scripts and then load the data separately. And this also allows you to split your large tables out. So what are the advantages of either of them? You can have SQL execution could be very slow because you need to perform SQL executions, insert statements from the SQL dump. And it is sequential in nature. It is slow because it is sequential in nature as well. You need to restart after failures. There are no checkpoints here. So if something goes wrong in the middle, you need to dump the whole thing out and then restart from beginning. And it is good for smaller database or tables, right? So you don't want to do it for large databases and tables, because if I have a 1,000,000 row table, I don't want to do an insert statement for 1,000,000 rows. That's not the right way to do it. When I use a flat file, it is faster and it can load files in parallel, because I can basically set a load command and the load will happen in parallel. And I can resume each file. So I don't have to really say that I need to start from the beginning if it fails. So if one of the file fails, I can always say, okay, hey, start from this file onwards. I have 10 files, the 8th file failed, I'll start from the 8th file onwards, because I can do checkpointing, and it's well suited for larger databases and tables. So when you do your consideration for importing from on-prem to RDS, always think about these factors. What do I need to do? What do I need to do on my source side? What do I need to do on my RDS side? And what do I need to do on my MySQL dump side as well? Because I want this to be really fast. Once the dump has been imported, what we will do is we will start the external replication. So I will position to start the replication point-in-time recovery from, and then what I'll do is I'll execute this command on the screen, the MySQL dump command. And once the MySQL dump is completed, I will start the replication user. I'll create a replication user on the master database, which may be running on-prem or on Amazon EC2. Once the database replication user has been created, what I would do is I would configure the replication target and start the replication. So if you look at this here, I am now calling certain stored procedures which are there in RDS today. So these stored procedures allow you to do common DBA tasks, which you would do with your commands in normal MySQL instances. So the RDS set external master is one of those procedures which allows you to set your replication source. So you would say the master for my slave is this server, and once the master has been set up, I would start the replication. Again, this is another RDS only package which is available to do common DBA tasks. So once the replication lag is near 0, what I would do is I'll stop the replication. I will promote this to a master by calling the RDS reset external master command. Point the app to the target Amazon RDS database instance, and you are all set to run. So this is for importing data from on-prem or EC2 into RDS. I'm already running on RDS. What do I do if I need to export this data from RDS into my on-prem server? There are many reasons I may want to do that. One of the reasons is I may want to do some testing on on-prem, or I may want to give a copy of a database to one of my partners so that he can work on it. I don't want to give him direct access to my RDS instance or to my AWS account. I want him to use his own account or use his own internal servers to do this. Or the third thing is I may want to actually do some kind of development. So I want to refresh my development instances with the latest data from production so that the developers also get to see the latest data in production. So how do I export data to an external source? So we follow the same process, right? I would take a dump data from my master database. I do a MySQL dump of it. There are two ways to do this. One is I can do it from the master itself if I need the actual real-time data, or I can take a backup, a point in time. I can do a point in time recovery to maybe 1 hour before the current time, and then take a backup from there. So if this is a test or a dev system, it doesn't really matter, right? Whether I'm giving them the real-time data or I'm giving them a 1 hour or 1 day old data. All they need is real life data, real life production data. That's what they need. So if they use the dump data command, they can use the dump data command either on the master database or on a point in time recovered database in RDS. Take this data onto a staging server, which is a EC2 instance on AWS. And from that EC2 instance, you basically do a SCP into your server on-prem and then load the data into your master, which is basically a MySQL dump. We already saw the considerations what you need to use, whether you want to use a MySQL dump with flat files or a MySQL dump with MySQL dump output on it. Once the data has been migrated and loaded, you can take your master and create a slave from the master to your on-prem so that the replication starts happening. So as I told you, right, you can take a 1 hour old point in time recovery and then take the data and move it there. And then if you want to catch up to the real-time data where you don't want to even lose like 1 hour of data on it, so you can catch up to the real-time data using this replication feature, which is available in MySQL RDS today. And once the catch-up is done, you can cut loose or continue to keep that as a slave running on-prem. So you would basically call the bin log retention hours to 48 hours so that you can continue to keep sending out bin log transactional data into the slave, and the slave can catch up to that. This is available in MySQL 5.6 on RDS today. This is not available for other versions of MySQL on RDS. You can also take your data in MySQL and sync them to Redshift. Why would I need to do that? So my production systems are on MySQL. My logs are getting generated with IDs that have pointers to the production system. So I have a ID which says what is my product ID that a customer is looking at. Instead of writing the product name into the log, to reduce the size of the log, I'm only writing the product IDs. So I write the product ID which the customer is looking at now, the product ID the customer is hovering on. So on an e-commerce site, I would like to collect that kind of information for doing analytics on it to find out, hey, which should I recommend to the customer? Why was he standing on this product for quite some time? Was he liking, did he buy the product and things like that? So this product ID to product name mapping is actually available in the MySQL database. I would want to take that data into my Redshift instance. So I would like to sync my data from RDS into Amazon Redshift. Amazon Redshift is our petabyte scale data warehouse, which we use to, you can connect it to Jaspersoft, Tableau, Business Objects, or any ODBC, JDBC compliant application and do really fast aggregated queries. As a columnar data warehouse, it allows you to aggregate faster, compress better, and return you data at a very low performance, with a very high performance at a low latency. How do I sync data from RDS to Amazon Redshift now? So I would basically go and use this in 5.6 MySQL again, only available with 5.6 MySQL. I would enable row-based logging. So I would say bin log format is row-based. So I would first enable row-based logging. Then I would take these bin logs on and apply them on Amazon Redshift. The bin logs can be formatted into insert commands and just fired into Amazon Redshift. Or you can use the Amazon partner solutions from Attenuity or Fly Data that will allow you to do this as well. So they will be able to automate this entire workflow for you where you take the data and push it to Redshift on a regular interval. Or as the changes keep happening, you can keep pushing data into the Redshift database as well. But remember, this is meant for smaller updates going in, not for your entire data coming in. When your entire data comes in, we would recommend that you load data into Redshift instead of doing applying the bin logs from Amazon Redshift. Perfect. So moving forward, let us talk about availability and disaster recovery. So we have 40% of RDS customers using multi-AZ today. Multi-AZ allows you to run your database in a master-slave mode with a synchronous replication between two availability zones. An availability zone is a collection of data centers with a unique point of failure. So an event in one availability zone doesn't affect the other availability zone. Running your application in two availability zone gives you high availability out of the box. And RDS, with a single click, you can convert a database from a single AZ into a multi-AZ, thereby increasing your availability of the database. Whenever there is a outage on the primary database, the failure detection happens in 25 seconds. We would detect a failure within 25 seconds. We would move the standby to, we promote the standby to a master. We convert that into a master. In 5 seconds, we convert that into a master. Once that is converted into a master, the DNS names are updated so that your application don't have to change. Your application does not have to change as soon as the DNS is updated. Your application doesn't have to change. So your application can continue to still hit the same endpoint that has been provided to you. And this DNS change takes 30 seconds. So DNS update plus crash recovery would take 30 seconds. And within 60 seconds, your application can now start working with the primary database, which was earlier a slave database. So again, your primary failed in AZ1. We detected the failure. We promoted the standby. Once we promoted the standby, we updated the DNS and did some crash recovery and made the database available to you within 60 seconds. And your application can start working with the primary database. After this, what happens is a new secondary database is created for the synchronous replication to continue so that you have high availability on your database. All this happens behind the scenes. You don't have to do anything for this to work. All you need to do is tell us that you need a multi-AZ database. And it's just a configuration setting. It can be either done through the console or done via the API call through the command line. We have multiple ways to do it. So once the primary comes up, then your secondary is also there for it to start doing synchronous replication. Your application may experience a 60-second outage. So you may want to do a exponential back off when you write to the database or read from the database so that you don't expose that failure to your end customer. So how does Read Replicas help us with availability? Your application continues to read from the primary database, and you are running read replicas, which are asynchronous replication from the primary to the read replica. Consistent reads happen from the primary, and writes always go to the primary. Eventually consistent reads come to the read replica. So example of a consistent read is what is my stock in hand for a particular product. Eventual consistent is how many orders were placed in the last 1 hour. That can be eventually consistent, right? I don't really need to, this is not something that needs to be read from the master. I can read it from the read replica. They are eventually consistent. I can have multiple read replicas from the primary so that the load on the read replicas is spread evenly across in the application. So the application can go on a round robin fashion reading from multiple read replicas and thereby reducing the contention on a single read replica. When the primary fails, we know that the secondary takes up and becomes the primary, and then the replication still continues into the read replica. But in 5.1 and 5.5, we see that the replication stops. The replication stops with this error. So on 5.5, you get a replication after failover error, which says that you cannot read from a binary log because you're asking me to start replication from an impossible position. So what we need to do is, you may need to do the sync bin log equal to 0 on 5.5. You may need to do a crash recovery, start a new bin log, and still process the position from the old bin log. So setting your sync bin log to 1 increases, has a performance hit of 2 to 4x on your performance. So we would recommend that you set your sync bin log to 0 and just knock the read replica out and create new read replicas for you to continue working. In 5.6, sync bin log is set to 1 by default. The bin log group commit improves performance, and crash safe slaves improve replica reliability. So the chart on the right hand side corner shows that if you set your 5.5 sync to 0 and you set your 5.5 sync to 1, you would see that there is a performance degradation there. And with a 5.5 sync to 5.6 sync to 0 or sync to 1, there is no performance degradation, visible performance degradation at all. So on the y-axis is the transactions per second. We are still able to do a consistent number of transactions per second on 5.6 with the sync bin log set to 1. More reasons for you to upgrade to 5.6. If you have not already done so, we give you a single click upgrade. We allow you to upgrade from 5.5 to 5.6 with a single click. So please feel free to use that to upgrade to 5.6. A lot of good features, a lot of performance enhancements in 5.6 that will help you run your application better. So how do I do disaster recovery using read replicas? So today we give you cross-region read replicas. So your cross-region read replicas allow you to set a read replica in another region. So for example, I can have US East as a region and US West as another region, and I can do a cross-region read replica between these two regions. The advantage of doing that is that if there is an issue with the AWS, the entire US East region, you're not able to make connectivity to it, or there's a tornado that has hit it, you still have your data in US West and you can connect to that application and use it. But remember, this application is not a synchronous replication. This replication is asynchronous replication, and this replication uses MySQL replication. It doesn't have any ways to make a synchronous replication here. So you already have an application connected to the primary from AZ1 and AZ2, and you have a synchronous replication happening on the secondary on AZ2. You connect this primary to the read replica in AZ1 in region 2. This may be US West, EU. If you take Singapore, it can be Singapore and Tokyo, or Singapore and Australia. It left you where you want to keep your region 2 in. When a disaster and the application running on region 2 also connects into the primary directly. So it doesn't connect to the database on the region 2. It only uses the region 2 database for getting eventually consistent reads. As we saw in the previous slide, all your eventually consistent reads can happen out of the read replica on region 2. This makes that closer to the application, and only writes go into the primary database. When disaster strikes on region 1, you promote your read replica to a primary database and point your application to that primary database. Once this is done, you may see that there is a bit of a data loss here, because asynchronous replication usually means that there is outstanding data that needs to move in to the database. So that outstanding data may get lost. It varies depending on the amount of transactions you are doing per minute on the master database. So based on that, the read replicas lag would increase or decrease. And this feature again is only available in MySQL 5.6. Cross-region read replicas are available only in MySQL 5.6 today, not available for 5.5. So let us talk about scale and performance. So before I get into the read to write ratio, I would like to mention a few things about RDS. So RDS allows you to scale up or down your capacity. You can scale up your capacity and scale down your capacity based on needs of your business. So I can start off with a M3 small medium instance, a M3 medium, and go up to an R3 8x large instance by a click of a button on the console. And I can come back to an M3 medium at a later point in time. So the scale is all online, and it doesn't affect your application in any which ways. When you run on a multi-AZ deployment, what happens is when you run on a multi-AZ deployment, your slave database upgrades first, and then we do a failover to the slave and then upgrade the primary database. This way your application continues to function as normal. On the storage side of things, MySQL we do an online scale storage, so you can scale your storage from 5 GB all the way up to 3 terabytes in size. So I can go from I can start with a 5 GB database because my business is small. You don't have to overcommit. You don't have to do capacity planning to find out after 6 months where would I be. You can start off at a 5 GB database or 10 gig database, which may be 20% of over what you need today, and then slowly go up as your business grows, as your database grows, and allows you to go up to 3 terabytes in size. Apart from scaling storage, you can also scale your IOPS. If you're using GP2 storage, then your IOPS will scale as you increase the volume size on the instance. Or you can use PIOPS volumes, where you can go and say, I want to have 1000 IOPS today and increase it to 2000 tomorrow. And there is a ratio that you need to still maintain between the amount of volume storage there and the IOPS that is needed. So scale is very simple in RDS, and we allow you to do almost everything online. So you really don't have to take your application down or ask your business to give you downtime to do these operations. The other thing is the scale of your eventually consistent reads. We saw that you can have multiple read replicas and scale your reads, your eventually consistent reads. So you can create read replicas which will allow you to bring up read replicas during month-end reporting cycles, so that you don't have to take a toll on your master database for doing this or increase the size of your master database. This will help you to scale your application based on seasonal variations. So month-end reporting, I'll have 4 read replicas which will handle the month-end reportings. Once the month-end reporting is done, I'll come back to a single read replica. Completely left to you how you want to do it, and there are a lot of architectural patterns that can help you achieve this. So read to write ratios. So we're talking about how read replicas increase your scale. So when I have 90% reads and 10% writes, I get to see a 1x scale by adding replicas to it. And as my number of reads are are spread out across the read replicas and the primary database, I'm able to really scale this to 2x, 3x reads, so that my reads, the maximum reads go to the read replicas and the minimum reads come into the primary. So as I'm just repeating this again because this is very important, the read replica is an asynchronous replication, so you will find that they are eventually consistent. So please don't use read replicas for getting your consistent reads. Okay, should I ship this order or not? Is there enough stock on hand so that I can approve this order? Please don't use read replicas for that. Use your primary database to satisfy those kind of reads, and use the replicas for anything else, right? I need a product listing. How many products are there satisfying a particular search condition and things like that. You can continue to use read replicas. So it gives you 3x scale, but if there are more writes than reads, you will see that your scale comes down, because more writes basically mean that the writes cannot go into the replicas, and also they increase the replication lag. The more writes are there, your reads become more consistent, eventually consistent. They are no more consistent for you. So the more the lag is, the more eventually consistent the reads are. So I'm not able to really achieve more scale if my reads increase. So this graph here shows you the scale based on percentage of writes. So if I do 10% writes, I'm able to scale well, compared to when I do a 50% writes, where my scale is really, really low. So this graph basically shows you that if you have more writes, then adding read replicas would not really solve the problem. You may want to look at the primary database, figure out whether you want to have increase the number of IOPS, increase the size of the instance, scale the instance so that you can get more throughput out of that instance. InnoDB cache swarming, again available only as of 5.6 today. It allows you to save the state of the buffer pool. Applications could respond faster after a DB restart because your buffer pool contents are saved, and when the DB restarts, it brings up the content from the file into memory. So benchmarks shows that we have a 4x improvement in TPS. So this benchmark is from the Yahoo Cloud Serving benchmark. So we see a 4x increase in TPS. So you take the buffer pool and dump the buffer pool into a disk, and from the disk you load the buffer pool back into the memory. So what is the kind of performance we're going to see? You see that the red lines are the warmed cache and the blue line is the unwarmed cache, and you see that the transactions per second, and this is the time after the restart, right? So after a restart, when I start sending transactions to the database, what is the transactions per second I'm getting? So you see that it takes 9 minutes for the InnoDB cache to warm up to serve that queries. So the InnoDB cache is actually a cache where your data blocks are stored, and these data blocks, as long as you don't read it from the disks and all the serving is happening out of memory, your transactions per second can increase a lot. And you see that there is a 4x improvement in performance when I use a warmed cache. When I start with the warmed cache, I can just straight away see a 4x improvement in performance from the 70th second itself. I don't even have to wait till 9 minutes for the whole cache to get warmed up. To enable InnoDB cache warming, again remember this is only available in MySQL 5.6, not available in other databases versions. So enable the InnoDB buffer pool dump at shutdown to 1 and InnoDB buffer pool load at startup to 1. So enabling this basically means that when I shut down my database, for some reason, I store the content of the buffer pool into flush them into a disk file, and when I load it from that file. Now this is super great, right? This is for predefined or maintenance windows that I need to do. So I have a maintenance window coming up. I know that I'm going to shut down the database. I'm going to start the database. Everything is fine. What happens if I don't know that? What happens if my database fails? unplanned failures. For unplanned failures, what you can do is you can create an event which basically scheduled every 1 hour and basically calls an RDS INODB buffer pool dump now command. So every time your database, every 1 hour, the event basically triggers and it just calls this command where the buffer pool is dumped into the disk. And whenever you want to, once your database comes up, you can always read from the buffer pool the file on the disk into memory as well. So next thing with performance is schema changes. Let it be enterprises or let it be startups, you would always see that your application is evolving. And if you don't innovate on your application, you're not going to go anywhere. You need to innovate on your application. Every day you need to innovate. And when you start innovating, you will see that there are certain things that you need to change on your database. One important thing that comes up is the schema changes. I do a schema change. I want to add a column to my table because that's a new column that I need to add. And adding a column, like everybody knows, is a very tedious task in a database. For really large tables, right? If the table is small with 100 rows, it doesn't matter. But if I have like a 3 GB table or like a 10 million rows or 100 million rows in it, then I need to really think through how I'm going to add this column because it's going to have a serious impact on the queries that are referencing these tables. And if it is a transaction table, even bad because there's a lock established on the table and the lock will prevent you from even writing into the table. So all your orders will come to a stop. So how do we go about doing this? The ways of doing this, we have multiple ways of doing this, and the considerations which we have to think about is ease of use. I need it to be very easy to do it. I don't want to make it really complicated. And I want it to be performance, and time to complete should be short, right? I don't want it to be like a 3-day downtime for completing this work. So what are the options available for me? I've got Read Replicas. I can do it through Read Replicas. I'll show you how to do it through Read Replicas now. Native 5.6 functionality. So if you're on 5.5, then you don't have an option to go there. But if you're on 5.6, then 5.6 gives you online schema change options, which allows you to change your schema on the fly. And you have third-party tools like Percona, right, which allows you to do this in real time. So let us look at the considerations against each of them. So how much time does it take? What is the ease in which I can do it, and what is the performance of each of this? So on using Read Replicas, you have a primary, you have a read-only replica, which you convert to a read-write. You promote it to a read-write. When you promote it to a read-write, your replication stops, and then you add the column province, and once the column has been added to the customer address table, what you do is you create another read replica out of it and promote this to be the master. So this would be the master, and this would have all your latest data in it, and this will also be able to do it in real time, almost real time, right? So what you would need is a very short amount of downtime because from the master, you can say, hey, I'm shutting my application down for 3 minutes. I promote the read replica, run the script, create another read replica for this master, and then connect the application to the master. So the whole thing can be scripted. You don't have to even do anything about it. You can script the whole thing. And the beauty is RDS allows you to change the name of your database. So once your primary database is over, the work is over with the primary database, and you have dropped it, you can convert this database to a different name, which is equivalent to what it was with the primary. So you don't have to change the application settings. So native MySQL 5.6 feature, easy to use, available by default. It is available on RDS. So there's no block DML in most cases. It's in place. You'd still need to do some amount of data reorganization. You cannot control throttle CPU or IO utilization. So as I was telling, in a 2 GB table, if I'm going to go and add a column, there is no way for me to say, okay, hey, this column addition should only take so much CPU and so much IO. It cannot consume everything that is available to it. And if you are running it on a replica, on a database that is already replicated, then you will see that there's an increase in the replica lag, because there is many bin logs entries that have to be flushed out. So you will see that there is an increase in the replica lag. Time to complete is relatively less, and we're going to see this in comparison to other options. The other way to do this is to use a Percona toolkit on EC2 on a remote host. You do a pt-online-schema-change, and you want to add a column province, and you want to add it on the customer address table with the password and username and password of this. And this would execute on the RDS. The challenges with this is you need to have an EC2 instance. You need to do an install of this because you need Perl modules which are for Percona. There is very less performance impact on this. We're going to see that as a graphical representation. The master load replication lag, so you can really do some amount of copy throttling as well. It could take longer. It is not going to take smaller amount of time because of the way that is online. It can take longer to complete as well. So this is a graph that shows you Percona versus native 5.6. On the y-axis, you have got the transactions per minute, and the x-axis you have got the timeline for these transactions. So you see that on Percona, when I do this in real time, I do an online schema change, I have a dip in the transactions per minute, and on native 5.6 I have a heavy dip on the transactions per second. So how much time are we talking here for this? On Percona, if I use Percona to do this, it takes 1 hour 48 minutes to do it. The process takes 1 hour 48 minutes, but remember this is non-intrusive. It's happening in parallel with the transactions per minute. On the other hand, with native 5.6, it takes 45 minutes to complete this work, but you see that there is a serious dip in the number of transactions that are running. So I go from 400,000 transactions per minute to 5,000 transactions per minute. Almost 5,000 or less than 5,000 at the last stages of the operation. So there is a performance impact to this. So keep this in mind when you're going to choose which one you want to do. Whether you want to take a very short downtime and do it on a Read Replica, which you can promote it to a master and get it done, or want to do it through Percona or native 5.6. But whatever option you choose, please test it. Very important that you test this on a UAT box or on a replicated master database before you actually go and apply this on production. Each database varies. The way that the database has been organized varies. So one size does not fit all. You still need to come up with a solution that will work for you. And you should try all the 3 options and then decide which one works best for you. So a comparison, side-by-side comparison of all the 3 options. You've got Read Replicas. Ease of use is not all that great because I need to shut down the master, convert it, call APIs and things like that. But with native MySQL 5.6 and Percona, we see that the ease of use is there. The native 5.6 is the most easiest to use because it's all available by default. I don't have to take downtime. I don't have to do anything. It just works. Whereas with Percona, I need to take a separate instance, install it, do the configuration and things like that. The performance on Read Replicas is super good, right? Because there is no impact at all. You may have a 3-minute downtime on your database, on your application, which can be on a Sunday midnight or something like that. But apart from that, it's almost real time. So the performance is very good. The native MySQL 5.6 performance, as you saw, is bad. It really takes a toll on your performance. Percona is not all that bad because it still allows us to run it, take a dip on the performance, but it's not as bad as native options. The last one is the time taken. Read Replicas are good for time taken as well because the amount of time it takes is maybe a few minutes. On native MySQL, the time taken is 45 minutes to do it. And on a Percona database, it's like 1 hour 48 minutes or go up or go down depending on the amount of data you are changing. So remember again, please test this before you get this into production. test everything because this is your production database and database is your lifeline. We don't want you to have a downtime on the database, unplanned downtime on the database. Please test it, make sure you're comfortable with which option works for you, and then use that option. So let us talk about burst modes in GP2 and T2. So we recently released GP2 with our EBS volumes, SSD-backed general purpose EBS volumes, which comes with 3 IOPS per GB of provisioned storage, which is the base performance that we provide. When you're not using the 3 IOPS per GB of provisioned storage, we will give you credits for not using it. So if you're not using it, we'll just keep storing that into a bucket, and we allow you to burst to 3000 IOPS when the need comes. So we're going to see in detail how this happens, and T2 is very similar to that. T2 is our instance type, which allows you to conserve CPU credits, CPU that you're not using. We conserve it for you and allow you to burst out on that as well. So there is a base performance plus burst. Earn credits per hour when below base performance. When you're not really performing, when your database is not being used, you earn credits for it. We can store up to 24 hours worth of credits, and beyond that we will overflow. And there are Amazon Cloud metrics to see credits and usage. So how much credit is left, how much is being used, how are you consuming the credits. You can see that in CloudWatch today. So burst mode and GP2 performance. So you see that the blue lines are the read IOPS and the red lines are the CPU utilization. So this is what we give you. 6,000 transactions per second is what is happening today. And the GP2 exhaust credits, when they exhaust the credits, we bring it down to 3,800 transactions per second. That's what we bring it down to. And once the T2 exhausts the CPU credits, you would see that is it lasted for quite some time. We bring down the CPU credits also on it so that you only get 2,200 TPS after that. So how does this credit work? So think of it like as a sink with a spout on the top, with an overflow spout on the top. And what happens is your credits which are not being used are put into this big sink. It keeps accumulating inside the sink, and once it reaches that spout, beyond that spout we don't accumulate it, we start overflowing it out and you lose those credits. But whenever your application needs it, we give from this sink up to 3,000 IOPS for your application to use. So we store up to 5.4 million IOPS in that sink and then give it to you at 3,000 IOPS for consistent performance of 3,000 IOPS when your application needs it. The same thing happens with CPU credits as well, but here we store it for 24 hours instead of having a number to that. We say we'll store it for 24 hours, and beyond that we will overflow. And whenever you need it, you just ask for it and we'll burst your performance for you. So T2 mediums, small, are great instances for small database workloads. And GP2s are equally good for small workloads. But if you are running a very big database, very transaction intensive database, which takes users 24/7, then you should also look at IOPS, which is the provisioned IOPS storage as well. Though they work out a bit expensive than GP2, sometimes those give you better performance than the GP2 ones because of the nature of your application. So here, if you look at it, as the CPU credit balance goes down, you will see that your transactions per second also keeps coming down. And as you exhaust your CPU credits, you will see that you have your transaction. It's getting a baseline performance. It doesn't anymore have a spiky performance. It gets a baseline performance on the graph. So the green graph actually shows you the CPU utilization, and the blue one is the credit balance that is remaining, and the red lines are the CPU credits that are getting utilized. So as your credit balance decreases, you will see that your utilization actually flattens out to a base performance. So let us look at some examples of burst mode versus standard versus provisioned IOPS here. So you see that on a DB M1 medium with a 200 GB standard magnetic disks, you get transactions per second of 1500 transactions per second. This is the baseline performance for this particular instance type and storage volume, and you pay around 57.5 cents per hour for this instance. If I use a M3 medium with a 2000 IOPS volume, with a 200 GB 2000 IOPS volume, I pay tad lower than my standard instance, which basically means that I should move away from standard EBS magnetic to IOPS volumes. I pay less, but I get an increased throughput, right? The reason for that is my M3 mediums are costed lower than M1 mediums, and they are only 40.8 cents an hour, and I get close to 2,500 transactions per second. My TPS are at 2,500, and again, this is a baseline. There is no increase or decrease on this. This is a baseline performance. We will provide you 2,000 IOPS anytime you ask for it. Then, if I bring in an M3 large, there's a very little increase on the transactions per second, and my cost is also increased by 10 cents. But for an increase in cost of 10 cents, I only get an increase of 500 transactions per second on it. So this is something you may want to consider, right? You may want to test it with multiple instances. Again, the cost of failure is very low on AWS, so you don't have to really say, hey, I'm going to commit myself to M3 large. You don't have to do that. You can take M3 medium, run it for a week, run M3 large for a week, compare these two, put it on a graph and compare it and say, hey, I'm not getting the performance for the money that I'm paying. So let me continue to keep it at M3 medium if my business is okay with that. The next option that we're going to look at is a T2 medium with a 200 GB GP2. You see that the T2 medium is actually priced at 10.5 cents per hour, but I'm able to start at a very high transactions per second. But as we saw in the previous slide, as my CPU credits and my IO credits keep getting exhausted, my transaction flattens out into a baseline, and that is way lower than the standard as well. So you may need to consider this, because if you're going to have consistently high QPS or TPS, then you would not want to run it on a T2 medium, because then you are not actually saving any credits. You are basically exhausting the credits as they come in. So it's better that you use T2 medium for burstable workloads. And when you burst, you are able to see that I'm even able to go beyond my M3 large performance. I'm able to do 3,500 transactions per second. Then I bring in a T2 medium with 1 TB of GB2. So the 1 TB of GB2 basically means that I get a consistent 3,000 IOPS. Because I give you 3 IOPS per GB of storage, and the maximum that a GP2 can provision the IOPS for you is 3,000. And if I have already provisioned a volume of 1 terabyte, my CPU credits never get exhausted. I always have CPU credits, and I'm able to give you a consistent throughput of 3,000 IOPS. And you see that I'm able to start at 6,000 transactions per second, and I fall down to around 4,000 transactions per second. This is because my CPU credits are getting exhausted. Remember, on the yellow line, both my CPU credits and my IO credits are getting exhausted. But on the dark blue line, you see that my CPU credit is only getting exhausted. So I'm able to consistently retain more transactions per second for a longer period. So I've got 6,000 for a longer period, then I've got 4,000 for a very long period. If you look at it, almost near 4,000 for a very long period. And then again I dip, and this time when I dip, I come and stop somewhere near the 2,500 mark. And what do I pay for this? I pay 23 cents an hour for this. And if you look at this, this is very close to your M3 medium with 2,000 IOPS on it. So this graph effectively says that choose the right instance for your workload. This graph is not aimed at telling you what instance you need to use. We are saying test it with multiple instances. Your application characteristics may be different than the other person's application characteristics. Please don't go blindly by somebody telling you, hey, it worked for me with a T2 medium, or it worked for me with a M3 large. please test it for your application. And when you test it, you would be able to really arrive at the correct instance type that you would need for your application workload. And you see the cost difference that you're able to save between the M3 medium with 2000 IOPS and the T2 medium with 1 TB GP2. They're almost close to 17 cents difference there. With 17 cents difference per hour, you're able to save 17 cents and get the same baseline performance that your M3 medium was able to give you. So you need to really test it out and then figure it out. And this is very simple with AWS. Let it be RDS, let it be Redshift, let it be DynamoDB. Coming to a value that works for our application is very simple because the cost of failure is very low. We don't really, it's all on demand, so you don't have to really commit on anything. You can run M3 medium for a week, T2 medium for a week, try out multiple options and say, hey, this is what works for me well. So let us manage the muck for you and keep your database running. So please don't try to do undifferentiated heavy lifting. You taking backups, you doing crash recoveries, you doing read replicas, or you doing synchronous replication is not going to differentiate your business from your other peers. What is going to differentiate your business is how fast is my query running, is my schemas optimized for my application, and let your DBAs do that for you. Leave the muck of managing backups and managing IOPS, giving you the right instance types to AWS. And we are there to help you. So if you are stuck with choosing the instance type, choosing the IO volumes that you need to use, please reach out to your account managers, reach out to your solutions architects, and we are more than happy to help you do the right things there. You focus on your business and do things that differentiate you. Please don't do anything that is undifferentiated. And RDS helps you achieve that. So you can try RDS for free. We give you RDS free of charge for a year. So please try RDS for free. You can learn more about RDS at our homepage. We have a very deep FAQ, and there are import guides available so that you can learn how to import data from AWS from on-prem or EC2 into RDS. Thanks a lot for attending this webinar. Your feedback is super important for us. It helps us to innovate and deliver this better next time around. So feel free to please complete the survey, send us your feedback, join the conversation at Twitter as well. Apart from these webinars, we also have online training, instructor-led classes, and AWS certifications that will help you to validate your technical expertise, give you a better foundation on the base concepts on AWS. Thank you guys for being a great audience. Hope you had a good time. Thank you.